Hi everyone, I hope you are doing well. So in today's video, I'll be going through the 2018 chemistry exam multiple choice section for the Northern Hemisphere. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah, let's smash through this paper. Question 1. All fuel cells are... Okay, let's understand a fuel cell. We know a fuel cell is what? It's pretty much a galvanic cell. And what does a galvanic cell do? It pretty much transfers chemical energy to electrical, pretty much. And we also know that it is a primary cell. What does a primary cell mean? It only discharges. So it can discharge, but it cannot be recharged. So it's also a... Yep. What else do we know about a fuel cell? We also know that we must continually supply reactants. It's not like, pretty much galvanic cells where reactants are stored and, when all those reactants finish and, galvanic, cell stops. Pretty much fuel cells, you have to continuously supply reactants. And that's the main thing about fuel cells. So they're very great and efficient. And we also know that, what else? We also know that they, don't create noise. We also know, and yeah, let's just see the options. Fuel cells are rechargeable. Absolutely not. We said that our primary cells, which cannot be recharged. So we can just pretty much get that wrong. Our galvanic cells, great. And the reactants are stored in the cell. No, the reactants are continually supplied. Are rechargeable? Absolutely not. Again, convert chemical energy to electrical? Yes. And the reactants are continually supplied. Perfect. Choose 1D. Next question. So we have this equation. The equation above is an example of what type of reaction. Well, what can we see? We can see this pretty much carboxylic acid. So let's draw it. So we have a C here. Goes like this. Carboxylic acid. Plus a alcohol. So OH. So these react, of course, it's pretty much like a in other words, condensation reaction, because what happens is this combines to create water. So they will create, H2O as we see here. And the byproduct, which is COOO HOC. Okay, we have this. Perfect. So, of course, it's a condensation reaction. Anytime you see water in the product side, it's always condensation. Whenever you see, water in the reactant side, that's hydrolysis. So that is the key here. Is it? Yep, so condensation looks right. Denaturation, absolutely not. Denaturation is pretty much the structure of the protein, or in this case, this over here, being dismembered. Well, the thing that might trick a lot of students is this H+. Now, normally, when you see H+, it's okay. There's a lot of H ions, so it's becoming acidic. It's like an acidic condition, hence the pH is changing. So, denaturation, when pH changes, isn't that denaturation? That's true, but not in this case. Be careful. Normally, denaturation occurs in proteins and all those other stuff, but not for this kind of... This here is a catalyst. Be careful. Have a look at it. It's a catalyst. It catalyzes a reaction. So, next was hydrolysis. Nope. For hydrolysis, the reactants must be on the left. Addition. Okay. If it was an addition reaction, we will only have one product. So what happens when addition is? Imagine this plus this. It always is one product, not two products. It's never two products when it's an addition reaction. So it can only be A. Nice and easy. Consider the following reaction. Okay, so we've given this reaction, given the Kc value and the temperature. Which of the following statement is correct? Okay. Kc is very large. The reaction is reversible. Well, okay, let's talk about it. Kc only changes through temperature. When you change temperature, the Kc value changes. Kc doesn't change because of pH, reactants, concentration. It doesn't react to anything. Only temperature. That's what I know for a fact. So only temp. It changes through temperature. That's one thing. And here it says Kc is very large. So if Kc is very large, the reaction is reversible. Well, let's calculate the Kc value for this reaction. All right. Perfect. So if Kc is very large, what do we know? If this value is very large, we know that there is more product than reactants. Okay, if there are more products, imagine more products are forming, and in other words, that makes it irreversible, because imagine like you're forming all this product and it doesn't go backwards. It only goes backwards. Imagine like, you only form little products. I say if Kc was small, it means that, you have a lot of reactants, but not a lot of products. What's going to happen? Well, some will become products, but because not all of them, there will be some, reversible reactions happening. So what we know, when Kc is very large, the reaction tends to be irreversible. That's a hint. Always remember that. When Kc is large, the reaction tends to be irreversible. So it's not A. Changing the pressure will affect the Kc value. No, remember, only temperature. Kc is very large. The reaction is effectively irreversible. Yeah, true. We can put that like that. Changing the temperature will not affect the Kc value. Absolutely not. Changing temperature will affect the Kc value. So I think only C would be the most suitable answer here. So yeah. Just remember, normally when Kc values are very large, the reaction tends to be irreversible. Question 4. The following diagram shows the energy profile for a reaction. So what do we know? We know it's endothermic because the change in H is positive. You remember, starting from the reactants, we end up in a product. So it is positive. A catalyst reduces the activation energy by 250 kilojoules per mole. Okay. The value of the enthalpy change in kilojoules per mole of the catalyzed reaction is what? Guys, let me tell you now. So catalyst does not ever affect the enthalpy change. Remember, a catalyst only affects the activation energy. Well, in this case, it says, what is the value of the enthalpy change of the catalyst reaction? It's not going to change. Let's really think about this. So when you actually catalyze this, it's, it starts, still at the reactants, and it's going to become, its activation energy gets less. It looks like this pretty much. So what do we see? Yes, well, the activation energy has decreased, but the enthalpy change has not decreased. Remember, still the same value. Always remember, enthalpy change does not change when you reduce activation energy. It's the same. So perfect. Well, in this case, it is positive. Of course, it's positive. What is the enthalpy change? Well, what's the difference between these here and here? It is, this is 1,000 minus 600. It is B. And make sure it's positive because it is an endothermic reaction. So, yeah. Question 5. Pentane, hexane, heptane, and octane are non-branch alkanes, okay? Which of the following statement gives a valid comparison? Octane has a greater viscosity and a higher boiling point than hexane. Okay, let's really look at this. Boiling point depends on the chain length. We know that. Boiling point, depends on the chain length. So let's start from the lowest. So what is the lowest in this case? It's pentane, because pentane is 5. So pentane is 5 carbons. Next one is hexane, which is 6 carbons. Going heptane, which is 7. And octane, which is 8 carbons. Perfect. So remember, the higher the carbon chain, the higher the boiling point, and pretty much the higher viscosity. Remember, viscosity is the rate of flow. So imagine having so much, remember the only forces that are acting on all these, non-branch alkanes are, dispersion forces, weak dispersion forces. So if you increase those branches, if you increase those carbon chains, what's happening is you're increasing the dispersion forces, hence pretty much creating a slower viscosity. Like a higher viscosity. Remember, viscosity is the rate of flow. So yeah, have I explained that really great? So remember, viscosity is the rate of flow. The higher the the carbon chain, the higher the viscosity and the higher the boiling point, pretty much. So octane has a greater viscosity and a higher boiling point than hexane. True, as you can see. We can put a tick on that. So pentane has a greater viscosity and a lower boiling point. Okay, so pentane does not, it does not have a greater viscosity and a lower boiling point than octane. Remember, octane has a greater boiling point because it has more carbons, and also it should also have, octane should also have a greater viscosity. So cannot be B. Peptane has a lower viscosity and higher boiling point. It does not have a higher boiling point than octane. So we can get that wrong. Heptane has a lower viscosity and a lower boiling point. So heptane is larger than pentane, so it should have a higher boiling point. That's wrong. So only A should be suitable in that question. So yeah, question 5A. Question 6. Some strips of metals, iron, zinc, and silver were placed in separate beakers, each containing one molar nickel sulfate, which is this solution at 25 degrees Celsius. What is the expected to occur over time? All right, so let's look at this. If they are all placed in separate beakers, so let's look at the first beaker. Let's say this is, your beaker 1. Okay, here is what? So it's going to be nickel plus, 2 plus solution. And so let's say the first one is actually iron. Let's place an iron metal here. And it's a solid. It's iron solid. That's your first beaker. Your second beaker, that's same thing. Well, actually, just let me copy this actually, because it's the same solution but different metal. Actually, just let me do this. What am I doing? There we go. And this here is zinc in this case. Okay. And the last one pretty much is, let me just copy this whole thing. Is a third beaker, which is silver. So let's drop silver here. And it's solid. Okay, so let's see which reactions will happen and which will not. So let's go to our data book, and let's go to our electrochemical series. Well, let's look at the first one. So first one, we have iron solid. Where is iron solid? Let's look at iron solid. Iron solid here. Perfect. Iron solid is right over here, as you can see. And where is nickel 2 plus? Nickel 2 plus is over here. There will be a reaction. There will be a spontaneous reaction, as you can see. They go like this. So there will be a spontaneous reaction. And so there will be a reaction appearing here. Perfect. Where what will happen? Well, because, this is going in this is going to be pretty much reduced. So it's going to create nickel, solid deposit. So this one will have nickel solid deposited into it. And some Fe2 plus ions, which are quite useless, so you don't. Next one, what about zinc and nickel 2 plus? Well, let's look at zinc. Where is zinc solid? It's just below over here. Yes, this also will have a reaction occurring. So again, still will have nickel deposited. So nickel deposited, and there will be a reaction. Next one, silver. So let's look at the silver. Where is silver? Ag. That's a problem. See, there wouldn't be a reaction over here. There's no reaction occurring. So, no reaction. Perfect. That's all we're going to need now. Let's see the answers. What is this expected to occur over time? Nickel will be deposited on all beakers. No, it will be deposited in these two over here, but not this one, because there's no reaction occurring. Nickel will not be deposited in any of them. No, there will be deposited. A reaction will occur only in beaker with the silver. No, so it can only be D. A reaction will occur only in the beaker containing iron and zinc. Yes, those are the only ones. So that's great. Let's look at question 7. Linoleic acid is a what? Polyunsaturated omega-6 fatty acid. Okay, so the way you just determine this is very easy. You just go look at your data book. Let's go down to our oh my god, where is it? Go down to our fatty acids over here. So what are we looking at? We're looking at linoleic acid. So it is this one. Where is it? This one over here, if I'm not mistaken. Yes, linoleic acid. Perfect. Let's have a look at it. To determine what omega is it omega-3, omega-6? The way you determine it is this. Have a look at this. So we start from this number, this carbon. How many carbons? So we have 1 carbon here. There are 4 carbons there. So imagine, now we have 5. And wherever the double bond occurs, that is the carbon. That tells us how much, what is it, omega-6, what number. So for example, this was 1. This is 4, so now we're up to 5. And here is where we first touch our double bond. So it's a 6, omega-6. So that's great. And it says, is it a polyunsaturated, monosaturated? Remember, unsaturated. What does unsaturated mean? It has double bonds or triple bonds. Saturated means no single bonds. But here we're talking about unsaturated. Of course, it's going to be unsaturated because we can see that there does exist some double bonds. But the way you determine if it's a mono or a poly, mono means 1 double bond, or whereas poly means more than 1. So because we have here, if you look at this here, which one is it? We have 2 double bonds occurring in here. It's going to be a poly. So pretty much question 7A. That's your answer. Easy. Coenzyme A is involved in the synthesis of fatty acids. Coenzyme A is what? Okay, what is a coenzyme? That's what you should first ask yourself. A coenzyme is, the way you actually explain it is by drawing it. So let's say you have an enzyme. Let's say we draw an enzyme like this. I don't know, something like this. Like that. Say this is your enzyme. A coenzyme is something that is like, it's like a little, organic compound that shoves itself into the enzyme. So this is your coenzyme. And for example, this would be your substrate. So what the coenzyme does is it shoves itself inside there, fixes up itself. So, it fills up the space over here. And now, whereas this substrate can now easily fit into this part over here and a reaction will occur. So, yeah, that's what it does pretty much. That's a fast, to understand what a coenzyme does. So let's use that to our advantage and answer this question. Is a vitamin that is a precursor of an enzyme? No, it's not a vitamin. So, B, the substrate. So, wait, coenzyme A is the substrate in the synthesis of fatty acids. No, it's not the substrate. It's like organic. This is the substrate. Whereas the coenzyme, it's by itself. So, no. Required by all enzymes to catalyze a reaction. No, some, reactions don't even need a coenzyme. So, when they always say all, that kind of should make you question, like, it's very, not most of the time when you see in chemistry it says required by all, start questioning. All? Are you serious? All? And yeah, most of them are wrong. So, D, a small organic molecule that forms a complex with an enzyme. Yes, it does. So, it shoves itself into the enzyme and forms a enzyme complex pretty much. And yeah. So, it would be D as your answer. 8D. Question 9. Before water treatment authorities release water into the environment, the water is tested to ensure it is safe and meets environmental standards. The concentration of organic carbon is one indicator of water quality. In an experiment, a student determines the concentration of organic carbon by conducting a redox titration between the organic carbon in a water sample and a standard acidified potassium. I can't even say this. Permanganate. Oh my god, I can't say solution. This solution pretty much. To accurately, we're talking about accuracy here, to accurately determine the concentration of organic compound, an action that the student should take is to what? Let's look at these. What is the student should take to increase its accuracy? Collect samples before and after storm. No, don't do that. So imagine it's a beautiful weather and, carbon, say the water is beautiful and it's nice, and you take a sample and then after, let's say, a rainy day and mud goes everywhere, goes in the water and just more carbon goes into it, and then you take it. It just pretty much affects your accuracy. You're just taking two different pretty much two different results pretty much. And yeah, that's not a good way for accuracy. So absolutely, it will just destroy your accuracy. Not a good way to think about it. Repeat the titration using different standard solutions. Yeah, it could work because there are many, standard solutions that you can use. So that does work, and it should also give you the same concentration. So repeating a titration using different standard solutions, if the concentration is the same for all, it pretty much increase your accuracy because the concentration should be the same, but using a different, a solution still, yeah. So B looks, could be right. So we're going to put a tick there. Using your measuring cylinder to measure the volumes of water sample. No. Measuring cylinder is not the best way to measure water volume. Using a pipette is the best way. It's more accurate. We're talking about accuracy here. So using a pipette or using a volumetric flask is much better than using a cylinder. Remember, using a measuring cylinder is not the best. So I wouldn't say that's great. Rinse the burette with deionized water before filling it with the standard acidified solution. No. Be careful here. The burette should never ever be, kind of rinsed with deionized water. And why is that? So when you rinse it with deionized water, there's going to be this water droplet. And when you shove that, standard acidified solution, the concentration of that solution actually decreases. So it's not in other words, it affects your accuracy. Be careful. Always, the burette should be rinsed with the actual solution itself. So this solution. So not the best one. So question 9B would be the best here. Question 10. So the diagram above represents the distribution of kinetic energies in a sample of gaseous reactant molecules. Activation energy, so this one, can be changed to activation energy this. This change increases the reaction rate. So an increase in reaction rate, okay. Which of the following gives the most likely cause of the change from E1 to E2 and explains why the reaction rate would increase? So let's look at here. What can we see? Well, we started, at this activation energy. Remember, what is the activation energy? So it's like this barrier that you must surpass. So something you need to get, so the reactants must surpass this energy for a reaction to occur. For example, let's look at this. This is a Max Boltzmann graph, and what the area represents is the number of molecules. So, okay, remember? Number of molecules. So if this is the energy, say, E1 is your energy, and of course, like we said, they must surpass this energy for a reaction to occur. So have a look here. This is the area for the actual ones that actually surpass that reaction. So only this little bit surpassed that energy and made that reaction occur. Whereas here, most of them didn't even have sufficient energy to even react. So yeah, that's the problem with E1. And what they've done is they've actually decreased the activation energy. And what really decreases activation energy? You should know straight away. Catalyst. A catalyst decreases in activation energy. So they'll likely use a catalyst to now make it E2. And now look here. Let's look at the area. So you can see that now more have this sufficient energy to overcome this activation energy and therefore react. So yeah, so I think the change they've done is they've added a catalyst. That's the most appropriate. And remember, a catalyst also increases that rate of reaction. So, yep, so a catalyst is added. Molecules move faster, resulting in more successful collision. Be careful, no. Every time you think about, when they say molecules move faster, think of it as temperature. Because temperature, when you increase temperature, you're increasing the kinetic energy, and yeah, when you increase the kinetic energy, molecules pretty much move faster. So be careful. A catalyst doesn't do that. So that's when you increase temperature. So when you increase temperature, this happens when molecules become faster because they have more kinetic energy. So not the best, eh? B, catalyst is added. True. And why the reaction increased? So greater proportion of reactants collide with sufficient energy to react. Best answer I could possibly say. Because yes, now there is much higher proportion of reactants colliding with the sufficient energy. You remember, sufficient energy to overcome that activation barrier for it to react. So I'll say B would be the best here. Well, let's look at C and D. So temperature increased. That's not the cause. When you increase temperature, what's going to happen is the graph becomes more like this. So it gets kind of curvier. And increasing more temperature, it becomes more, So in other words, that's not the change. The only change that could do decrease the activation energy is a catalyst. So that's wrong. Concentration of reactant is increased. No, don't ever think of increasing concentration will decrease the activation barrier. So that's it. Question 11. An aqueous solution of ethanol, so we have this, left exposed to the air, will undergo a redox reaction with oxygen to form ethanoic acid. The half equation for the oxidation reaction is what? When I'm actually seeing this, and you know what kind of reminds me? It reminds me of a fuel cell. Because when you see a fuel cell, what do we know? We know it's like a fuel, say a fuel, which in this case is ethanol, so ethanol. And then, the oxygen is also, shoved in there, so the O2 gas. And what do we know? Whenever in a fuel cell there's oxygen gas reacting, it is always the cathode. So remember, the cathode, where reduction occurs. Here, because ethanol is the fuel, it is going to be the anode, where oxidation occurs. Okay, that's what just comes into mind. So the half equation for the oxidation reaction is what? Well, when we're talking about oxidation, it's going to be ethanol most likely, so it's not going to be this oxygen gas. So, and it's already given you a hint here. Electrons are always supposed to be on the right when it's oxidation reaction. So, hint, 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 it can only be these two here because the electrons are on the right. So don't even worry about those. So we don't even need this diagram to help us around. So let's look at these ones. And okay. So which one would it be normally? Well, let's think about it. Okay. So we're going from this ethanol to ethanoic acid. So let's think about that. So we're going from CH3, CH2, OH, that goes to CH3, COOH. Now let's think. What environment is this going through? Well, it's acidic because ethanol tends to be, it's an acid and it goes through acid. So most likely an acidic condition. So we can actually add some water and H plus ions. So let's think about this. How many carbons do we have on the right and left? Well, we have 2 here and we have 2 here. Beautiful. How many oxygens? And we have 2 here and we have 1 here. That's a problem. So we're going to add a water. H2O. Now we have 3. No, my apologies. What have I done here? The water's supposed to be on the left because we have 2 here and we have 1 there. So H2O. Okay. So then we have 2. Great. Now how many hydrogens? We have 4 here. And we have 3, 4, 5, 6, 7, 8. We have 8 here hydrogens and we have 4 here. So we're going to add 4H plus here to compensate for that. And that's it. Now, let's think about this. So when we're talking about electrons, okay, what's the charge here? Overall charge, it's 0 because there is no charge here. Whereas here, well, this one has no charge. This one has. It's a plus. So imagine, that plus times 4. So there's a positive 4 charge overall on the right, and there's 0. Now, how do we compensate for that? How do we make them equal? Well, if we add 4 electrons on here, this, becomes 0. So, great. And that's it. This is your reaction, pretty much. So, let's see which one looks great. Looks like C is your best answer there. Beautiful. When you do pass exams, remember, guys, make sure you know how to deal with, simplifying, balancing, and, doing these redox reactions for acidic and basic conditions for these reactions. It tends to come up in many practice exams, so make sure you do those. So let's look at the next question. The semi-structural formula for the isomer, this is that. The correct systematic name for this molecule is what? Okay, so let's just draw it. So it's an N here, so it's a H here. This is an amine group. CH here, CH3 here, H here, CH here, and OH. Okay, so, well, let's think about the functional groups. The way we name these is by functional groups. Which one has the highest priority? Hint, hint, hint. it's always the one that has most oxygens. Like, for example, if it's a carboxylic acid or a alcohol, because, carboxylic has 2 oxygens, we would take that as a higher priority. Well, in this case, amine is very low in priority. It's this one over here. It's the alcohol. So it has to, and how many, sorry, wait, did I draw wrong? Wait, oh, my apologies. I just saw I made a mistake here. What did I do here? Simple mistake. I did a C here, forgot the C. Is that right? C. Yes, okay, perfect. So this has the highest priority, so it's going to be a ol. And how many carbons? Because I just had a look at these, I'm like, there is no pent. So I thought I had made a mistake. Yeah, I have. So how many? Well, we have 1. We're going to start from the highest priority, which is alcohol. So 1, 2, 3, and 4. That's the highest. So it's going to be a butane. 1 ol, because this occurs at the first carbon. Yeah, so which one has that? Well, only B actually looks like it has butane 1 ol. The other one has pentan 1 ol. That's wrong. This one has butane 1 amine. Absolutely wrong. And this one has, I don't know what the hell this is, 2-methyl-4-ammoon. It's too much. Rubbish. So B. All right. Question 13. Which of the following reactions has the lowest percentage atom economy for the production of ethanol? Okay. You should know, if you look at your formula sheet, let's have a look at this. So your data book. What is percentage economy? Let's have a look at it. What is the formula? Well, it's over here. This is what it is. This is going to help you work. So the way what is our desired product? Well, in this case, it's ethanol for each, it's ethanol for each of these. So it's this one over here, this one over here, this one, and this one. So we need to calculate those. So we want to, well, the formula is molar mass of desired product, which in this case is our ethanol, and the molar mass divided by the molar mass of all reactants, okay, and times it by 100, so get it in terms of percentage. So let's do that. Let's do that for the first reaction. All right, so we have ethanol. So ethanol, what is its molar mass? C2H5OH. So it's going to be, because we have 2 carbons, so 2 times 12 plus, how many hydrogens? We have 6, plus 1 oxygen, which is a plus 16. And that gives me 46. Great. What about this? What is the reactants in this case? What is the molar mass? Well, for this one, we have, in terms of all of this, we have 2 carbons, so 2 times, oh, what am I doing? My apologies. This is 100%. The first one is 100%. It's because both sides have the same, like this one has 2 carbons, this one, has 6 hydrogens, and this has 1 oxygen. So both of them have, so this should be 100. And it makes sense because remember, it's what is our desired product? It's this one over here. So imagine like we have 2 C's plus 6 H's plus oxygens, all divided by this. How many carbons? So 2 C's we have in this case. How many hydrogens? We have 6 and 1 oxygen. And that is just equal to 1. And imagine times it by 100, that's 100%. So that is 100%. Remember, we want the lowest. So yeah, that's that. What was I thinking? Yeah. Oh my God, you could have done that quick. The other ones is a problem because, now we have some, this. So we're looking at this. Remember, multiply by 2. Remember, we're talking about atom economy. How many atoms? So you need to multiply by 2. So if we know this is 46, imagine multiplying by 2. So what is 46 times 2? That is 92. Divided by this over here, which is glucose. So how many carbons? So we have 6 times 12 plus 6 times 16 and plus how many hydrogens? We have 12. So that's 180. And then times it by 100 to see the atom economy. So 92, 180 times 100. That gives me 51% pretty much. Done. Easy. Next question. Okay, so it's this over here, which is just 46. That's your molar mass. What about this? Ooh, that's a long. So how many carbons? So we have 2 carbons, so 2 times 12, plus how many hydrogens? We have 6. We have 6 hydrogens. Plus, how many oxygens? We have 1, so it'll be 16. And now we also have chlorine and sodium, and I don't know what the hell their molar masses is, and we can check that by looking at our periodic table. So I'm so sorry you can't see this because I can't tilt it, but in terms of sodium, Na, sodium has 23, so we can write that, and chlorine, which should be on the left, has 35.5, so 35.5. Imagine adding that, that's, okay, got it. It is 104.5. So 104.5 times 100. So that's 44%. Okay, great. And let's check the last one. Well, the last one is, again, it's ethanol. That's our side product, which is a 46, divided by what is this overall. So we have how many carbons again? So we have 2 carbons, so 2 times 12, plus how many hydrogens? We have 5, 6, 7, 8 hydrogens, plus how many oxygens? We have 2, so 2 times 16. And how many nitrogens? We have 2 nitrogens, and I believe nitrogen, if I'm not mistaken, 2 times, so nitrogen is 14. Enter, so that gives us 92. So times that by 100. That's 50%. Okay, so the lowest in percentage, in terms of the lowest percentage atom economy, is C. So question 13 is C. Perfect. Question 14. The following 2 spectra were obtained for a pure organic substance, compound W. So we have, the carbon NMR, which tells us that there are 3 peaks, meaning that there are 3 carbon environments. Remember, 3 carbon environments. Okay, that's important. Easy. Next question. Infrared spectrum. You should know that infrared spectrum, what does it give us? It gives us the functional groups. What functional groups does the compound have? So we'll look at it after. Well, let's look at the questions. The formula for compound W that is consistent with the spectra above is what? Well, let's first draw the first one. Let's draw all of them first. So we have this one over here. Let's draw that. So it's a C. And I think, so we have a C here, like that. And a C here. Oh my god. Why do they make our life harder? Just make it like this. COH here. H here. H here. C here. H here. H here. C, H here, and H here. And an OH. Okay. Now, let's look at the carbon environments for this. The way you determine carbon environment is by symmetry. So, for example, well, this is symmetrical. As you can see, this over here is symmetrical to this. Can you see? So we consider those 1 carbon environment. And then, this one also is another carbon environment. So there's 2 carbon environments. That's rubbish because in our spectra, it says 3 carbon environments. So A is rubbish. So we don't even think about A. Don't even look at A. That was easy, actually. I love that. Let's look at the next one. So it's a carbon 3, it's a CH here, a carboxylic acid here. So how many carbon environments does this have? There is no symmetry, so we have this carbon here, which gives us this carbon, and this carbon. So we have 3 carbons. Okay, let's put a tick there, that's consistent. Let's check the other one. The next one is a C here, C, double O here, O. So it's an ester group, pretty much. And so how many carbon environments? Well, because there's no symmetry, this one, sorry, my apologies. This one and this one. So there's only 3. That's great. That also fits our requirement. And the last one. So we have a C here. C, pretty much double O, C. So it's a ketone. Now there is symmetry here. Look at the symmetry. This and this is mirror image to this. So we consider those 2 as 1 and then this as a second. So there's only 2 common environments. So that's rubbish. We only need, there's supposed to be 3. So we can actually get B or C. That's the only possible answers. Well, what's B? Well, B, we remember it is a acid, carboxylic acid. Whereas what? This one here is a ester group. Am I saying it right? Ester. Just the ester group. Well, let's look at the peaks. Well, we know that there is the reference, the finger point section, which is around 1400, which we don't look. So imagine like forgetting all about this. What is the peak? Well, the peak that looks in my eyes is this one. And let's look at carboxylic acid. The way we look at, let's try carboxylic acid. So what I'm going to do is I'm going to go look at my my data book and go down to my infrared spectra over here. So let's look at acids. Where is acids? Aha! Acid, this one. And there's supposed to be a peak around here, which is 1680. So what's that? 1680. So that's 6 here. 1680 is around here to 6 740 around here. Am I a mistake? So 6 is here, 1680 around, and 1740 is around here. There is no peak here. So, but it's okay. That's no problem. I will check the other acids. Remember, there's still more we have to look at. Look at this acid over here. There's supposed to be a peak at 250. So, that's 2500 here. There's no peak looking, and 350. So, over here. It's only this little peak. That's not good. So it doesn't look actually like a carboxylic acid. Let's try a ester group. Let's try that. So try from here. Is there any ester? Nope. Well, only this one over here is the ester group, which is here. Let's check that. So 1720, 5, 6, 7. So around here, 17 and 184. So here. Beautiful. As you can see, that is where the peak is. So it is pretty much an ester group. So it can only be C as your answer for that one. Oops, let's let me. So what question is this? Yeah, question 14, C. Question 15. A zinc carbon dry cell battery has a potential of 1.5 volts, measured at standard conditions. The two half reactions that occur in these batteries are shown in the equation. Okay, so this is your oxidation. As you can see, the electrons are on the right, and this one has to be your, because the electrons are on the left, this is your reduction. Assuming standard conditions, the electrode potential of equation 2 is what? So what is the voltage for equation 2? Remember, the way I always tell students, the formula is what? Voltage, your voltage is what? It's the voltage of the reduction, so the highest in the electrochemical series, minus oxidation. So which one? Let's think about this. So in this case, well, our final voltage is what? It's 1.5. So we can write 1.5 here. Is equal to reduction. Well, in this case, this is our reduction, which we don't know. We'll call it X actually. Minus your oxidation, which is zinc. So what is zinc? We go zinc. What is its number? Let's look at zinc. There we go. Zinc is over here, which has a number of negative 0.76. Okay. And so, doing some algebra, so you'll get 1.5, x plus 0.76, and you bring this 0.76 to the left, so 1.5 minus 0.76 equals x, and that's going to give you your voltage for the reduction. 1.5 minus 0.76, and that gives me 0.74. So B as my answer for that one. Easy. Question 16. Which of the following compounds can exist as a cis or a trans isomer? Remember, okay, this is our way. It's much easier to draw them in the skeletal structure, because remember, so a cis looks like this. So you have a double bond, and we kind of have this. So this is a cis, because both are on the same side. And for a trans, it's going to have a double bond, one's up and the other one's on the so they're different directions. So this is what we call a trans. Well, if I was drawing this, which is what? So if I was drawing that, it's a double bond, and we have two carbons here, two carbons. This is just this, by the way. It just looks like this in terms of skeletal structure. It doesn't even exist as a cis and a trans. So it doesn't even look like these. Wouldn't even look like these. So that's rubbish. The next one is we have a carbon. So we have H's here, and we have a H here, and we have a CH3 here. This one will exist as two carbon chains here and a branch here. this does not look like any of these. If there was another branch like a CH3 here, yes, but unfortunately it doesn't. It looks like this. So B is wrong. D, so we have 3 here, C, probably double bond, so that and that, and a CH3 there. So if I was drawing this, it has a double bond here, and it could possibly have one that goes up, this one, and also this one could be an up, or it could be the opposite way. It could be up, or the other one can go down. So it could both exist as a cis and trans. So C actually looks generally great. So I would say C is the best one here. Well, we have to make sure that's right by looking at the final answer. So it's just this. Oh, no. What am I doing? This looks like a fatty acid, and there's no like a double bond. There's no double bond. So D is absolutely wrong. So 16C. Question 17. Soda water is made by dissolving pressurized carbon dioxide, CO2, in water. Okay, makes sense. A bottle of soda water was placed on an electronic balanced. The cap was removed and placed next to the bottle of the electronic balance. Okay, makes sense. So imagine we have electronic balance here, and we have a soda bottle. Let's say this is the bottle. It looks like this. Not the best drawer, but it looks like this. And they've took this cap off, and because, if you take cap, we're losing mass. So they're like, no, we're not going to do. We're going to put that cap here. So, but of course, mass is going to be lost because carbon dioxide will be coming out, and it's that fizz. It's like, it comes out, and that's carbon dioxide coming out. So overall, the mass will still decrease because carbon dioxide is decreasing. So as you can see, the cap was removed and placed to the electronic balance. It makes sense. The graph below shows the change in mass of CO2 escaping. The experiment was concluded at standard laboratory conditions. Okay. Assuming CO2 was the only gas given off, the volume of CO2 that was released is closest to 1. Now, we know that, when you open a bottle, like a soda bottle, and it's like, and it releases CO2 quickly. As you can see, it kind of gradually decreases. And at some point, it's going to stop, fizzing. It's going to, when you drink it, it tastes like piss most of the time. When you drink, like, Coke when there's no fizz. And so when you take that bottle off and when you drink it, it's so nice because it's refreshing because it has a lot of CO2. But after you leave it after some time, what's going to happen is, of course, that fizz CO2 has decreased, and then as you can see, as you take the time, the CO2 decreases, and then it becomes constant. And pretty much that point is like it tastes like piss, pretty much. It doesn't taste like it. Yeah. So what is the decrease in CO2 in this case? Well, we started initially with 1375 grams of CO2, and then we've decreased to this constant value of 1350. So what is that change? So what's that decrease? Well, the decrease is 25 grams, pretty much. There is a decrease in 25 grams. So, and this is your mass of CO2. So, of course, because we're talking about SLC, we want the volume. So remember the formula for SLC is what? It's N is equal to V over Vm, where Vm is the constant. So we need to find the mole of CO2. So the way we do that is mass over the molar mass. And what's the molar mass? It's easy. We know that carbon is just 12, and there's 2 oxygen, so it'll be this. So let's read that. 25 divided by 12 plus 16 times 2, and that gives us 0.56. So we can say 0.5681 is equal to the volume over the Vm, which is, in this case, it's in your formula sheet, which is 24.8. So, multiplying that by 24.8, and that gives me 14.1 liters of CO2 that is released. So A is your answer there. It's such a beautiful question, actually. I really enjoyed this question. It's nice and easy, I'd say. Question 18, the equation for cellular respiration is as follows. Okay, beautiful. So you should know that cellular respiration is an exothermic reaction as it's shown through the enthalpy change as it's negative. Okay, we've given the molar mass of glucose, which is this over here. When 72 grams of glucose is metabolized in cellular respiration, the total energy released is this. The value of change in H in kilojoules per mole for this equation is what? Okay. Well, the change in H, because it's measured in kilojoules per mole, it's like, using this formula, kilojoules per mole. And that's going to give our change in H. So what's the energy? We need energy in terms of kilojoules. So how do we get that? Well, we know that when 72 grams of glucose is metabolized, there is a total energy of this in terms of kilojoules that it's released. So we can write change in H because we have this much in terms of kilojoules. So we write that down. 1.126 times 10 to the power 3 divided by in terms of mole. What is the mole of glucose? Well, we have the mass of glucose, and it's very easy to find the molar mass because remember the mole of glucose, which I'm just going to write glucose actually here because I can't be word here, is what? It's the mass, which in this case is 72, divided by the molar mass, which is 180. So 72 divided by 180, and that gives me 0.4. So imagine putting 0.4 mole over here. And that's it. You divide those and that should give you your change in H, your enthalpy change. And remember, it is negative, as luckily they've shown us here. And yeah, so let's do that. So we're saying 1.126 times to the power of 3 answer. And that gives us 2815, and make sure it's negative. Yeah, kilojoules per mole. Only the C looks right because it has 2.86. So yeah, C is your answer. Question 19. The following reaction in which dinitrogen tetroxide, which is this, is converted to nitrogen dioxide, forms an equilibrium. At a given temperature, the equilibrium constant for this reaction is this. So this is your Kc value. So Kc is 3.15 mole. And the molar concentration of N2O4 at equilibrium is that. So you're pretty much, your concentration of N2O4 is 0.350. At this temperature, the molar concentration of NO2 at equilibrium is what? It's such a beautiful question. We know that Kc, you should know that Kc is what? Well, it's the product, so NO2. What's the coefficient? It's 2, so it gets squared, divided by that N2O4, the reactants. Well, we know the Kc is 3.15 at that temperature, and we want to find NO2, the concentration of NO2, and we know that N2O4 is 0.350, so easy, make a formula, multiply this, and then take the square root of the answer, and that gives you NO2, the concentration. So let's do that. So 3.15 times 0.350, and then take the square root of the answer, and that gives me 1.0, sorry, so NO2 1.05 mole. Looks like B is your answer. A meal containing a mixture of carbohydrates, fats, and proteins is eaten. The biomolecules in these meals are broken down into smaller molecules in the body before they can be absorbed. Which of the following summarizes the chemical reactions that would occur prior to the smaller molecules being absorbed by the body? Okay, before the body absorbs them pretty much, what happens is they get broken down. And what do we know? We know that carbs, fats, and proteins, the way they break down is through what reaction? Hydrolysis. Remember, breaking down of carbs, pretty much proteins, fats, is through hydrolysis. So remember that. So it can only be A or C. So B and D are wrong. Remember, condensation is, it's the formation. So yeah, it's a formation of molecules. So be careful with that. H2O is a reactant. Okay, remember, so in hydrolysis, we need H2O. We actually react it. It's a reactant. So hydrolysis needs H2O. Whereas condensation, water is a byproduct. So yes, we do need H2O. So yeah, the only possible answer is A, because it says hydrolysis, H2O, and the possible product glycine, which is true. Glycine is an amino acid, and yeah, it's so imagine protein, so say a random protein, it goes through hydrolysis, so we break down its molecule to its simpler pieces, which are amino acids, and yeah, we use H2O and as a reactant, and it goes through hydrolysis. Beautiful. Question 21. Which of the following produces heat energy as its main energy output? So we have, this one looks like a galvanic cell. Also this one. This one. Okay, we have that. And we have this one. All right. Well, the first thing I would say is see if the reactions are possible. Like, is there going to be a reaction occurring? So let's go to our electrochemical series. Now we know, remember, galvanic cell, the main focus of a galvanic cell is it converts chemical energy to electrical energy. So if we want heat as our main energy, so let's actually try this out. Let's try the first one, A. So we have what? We have copper. Where is copper? Copper's right over here. Beautiful. And iron. So Fe, which is this one. Beautiful. There is going to be a reaction where there's going to be a reaction between. So, yep. So it's going to be copper 2+. It forms copper solids. And so there is going to be a spontaneous reaction. And if there is a spontaneous reaction, we know that chemical energy is being converted to electrical energy. So the main output of this is going to be electrical energy. So I want to say it's A. A wouldn't be the best here in this case. What about B? So we have nickel solid, as you can see. It's a solid. It's like a metal piece. So let's look at nickel. This nickel solid over here gets reacted with zinc. It's like a solution, so it's a zinc 2+. In this case, it will be this. Is there a reaction occurring? No, there is no reaction occurring, as you can see. So what do we know? If there's no reaction, there's no reaction, so there's no even heat being produced. So I wouldn't say that. What about C? So we have cobalt and Pb. I call it Pb because I've, where's Pb? Pb is over here, and we have CO, which is this cobalt. So is there going to be a reaction? Yes, there is going to be a reaction between the Pb2+ and the cobalt solid. So if there is a spontaneous reaction, we know that, remember, in a galvanic cell, it's chemical energy to electrical energy. So the main output energy in this case will be electrical, so not heat. Let's try D as your final. D should be the answer, by the way. In a real exam, you should straight away pick D, but I want to really show you what's going to happen. So if we have aluminium solid, so this over here, with iron 2+, there is going to be a reaction. But you gotta remember, what is the possible? What's the point of a reaction if this occurs? If there's a reaction, the only main thing it's gonna be heat. It's produced. It's gonna be like there's a spontaneous reaction and there's gonna be heat produced. It's not like there's a wiring where we take all that chemical energy and we convert it into electrical. All that chemical energy will be converted to thermal energy, heat energy. So only D would be your possible answer here. There's nothing. There's no wiring. We're not actually so it wouldn't be D would be best in that case. All right, so I hope that's right. So 21D. Question 22. A 12-gram sample of vegetable is estimated to have a vitamin concentration of 30 milligrams or per 100 grams. So for every 100 grams, we have it's supposed to be expected that there's 30 milligrams of vitamin C. The high-performance liquid chromatography, HPLC, instrument used for the analysis produces a linear calibration curve for vitamin C concentrations between 0.02 milligrams per mil and that. Which of the following volumetric flask made up below mark would be appropriate for producing the vegetable sample solution for analysis? So what this tells us is these over here are what? So the true value of the concentration of vitamin C in, that 12-gram sample is supposed to be around, these over here, these values. So, okay. And because we're using, so we know that for every 100 grams, there's an expected value of 30 milligrams of, vitamin C. But we're using 12 grams. So how much expected vitamin C is 12 grams? Well, we'll use ratios here. For example, here, if we know that there is 30 milligrams for every 100 grams. In this case, we have 12 grams, so it's going to be over here. And how many milligrams of, vitamin C is supposed to be expected? That's easy. You just multiply this by that, and we get so what's 30, 100 times 12? And that gives me 3.6. So the expected value, no, the expected concentration of vitamin C in that 12-gram sample is supposed to be 3.6 milligrams, okay? So, because the units here are milligrams per milliliter, what I can say is like, let's say we pick the first one, 25 milliliter. Let's say we use a 25 milliliter flask. So, let's say this is our true value. It's supposed to be around, so if we know that this here is 0.020 milligrams per milliliter, if I'm using a 25 milliliter, so if I put here 25, and I find how many milligrams, so 25 times 0.020, that gives me 0.5. So in this case here we have 0.5 milligrams, so it's a between that to what? We do the same for the other one, so we have this, so 0.10, it's milligrams per milliliter, and we're using, remember, 25 milliliters, so it'll be 25 times 0.1, and that gives me 2.5. So this is the range. If we use a 25 milliliter, the true value should be around this, so that's where the range is, but that's rubbish. It's 3.6, it's more than, it's not even in between these two values. It's actually more than that. So a 25 milliliter wouldn't be the best in this case. So it's all right. Let's try 100 milliliters. So again, using this, so 0.020, remember milligrams and per milliliters, which in this case is 100. So it's 100 times 0.020. That's, so it'll be 2 milligrams to, we rub this and we're using, 0.10. To 10, so 100 times 0.1, so to 10 milligrams. Yes, that is in between that, so could be a possible answer. We're gonna put a tick in this, but let's try the other ones first, actually. So, the next one is a 25 milliliter, so imagine 0.020 milligram per 250, so what's 250 times 0.020? That's 5 milligrams. I'm not going to try the other one. If this is 5, the other one's going to be greater. So this is not even between that. So C would be wrong. And let's try the last one, which is, sorry, my apologies. Why did I rub that one? 0.020. We're using a 500 milliliter. So if I'm using a 500 milliliter, 500 times 0.020, that's 10 milligrams to some large value, which is still not between that. So the only possible answer would be B in that one. Nice. Hope that helps you understand that. Next question. Question 23. So we have here, okay, a mass spectrum. So the mass spectrum shown is for a molecule with a molecular formula this. Which species is responsible for the base peak? So the way I will actually determine this is, okay, let's look at what is the mass to charge ratio, which will, it's the same as the molar mass pretty much. So this is your base peak. Remember, this is your base peak. Don't forget, base peak, this is your molecular base, peak, but this is your actual base peak. It's the largest one, and it tends to be in the middle. So what is the value of the mass to charge ratio? 51, 52, 53, 54, 54, 55. So 55 mass to Z ratio. Remember, that's the same as molar mass. So imagine just rubbing this, and it's like molar, like the molar mass. So molar. What am I doing? Grams per mole. Oh my god. Wait. So what's the unit for that? Is it, so N equals mass over molar mass? It's grams per mole. Okay, that. So if we have that, we just need to check if these species have this over here. So let's try that. So let's try the first one. So we have 4 carbons, so 4 times 12, plus how many hydrogens? We have 7, plus chlorine, which is 3.5. That gives me 90.5. Large, very large. Next one. 3 times 12, plus 4 hydrogens, plus chlorine, which is 35.5. That's 75.5. Wrong. Next one. 3 times 12 plus 5. That gives me 41 less than expected. So let's try D. I hope D is right. 4 times 12 plus 7. 55. Perfect. D is the answer. Nice and easy, actually. That was very good. Question 24. An electroplating cell contains 2 platinum electrodes and an electroplating solution operating at 5 amps for 600 seconds. After the cell is turned off, 0.54 grams of metal is found to have been deposited on the cathode. Which electroplating solution was used in this process? The way that I would do this is, okay, I know that the charge is equal to the current times the time, which is in your formula sheet, which in this case is what? The current is 5, the time is 600 seconds, which gives us what? So what's 5 times 600? And that gives me 3,000, okay, coulombs. And I also know that the number of electrons, the mole of electrons is what? It's the charge over the Faraday's constant, which is also found in your data book. So it'll be 3,000 divided by Faraday's constant, which is 96,500. And so doing that on my calculator, that gives me and so the mole of electron is 0.0310 mole. Perfect. That is a hint. I'm just gonna rub this all off. That's all we're going to use here. This is the most important thing. Because what I'm going to do is, okay, this here, what is the chemical equation? Like, this here is silver, so it'll be Ag plus E minus goes to Ag, like solids. So, say we have 0.54 grams of metal, which is, in this case, we want to find the mole. So, and if we find the mole of Ag solid, we can multiply it to find, because it's a 1-to-1 ratio, it should be the same. It should be this mole over here. So it'll be, what's number of mole of Ag? Which is 0.54 divided by Ag. What is Ag? What is it? What is the molar mass of Ag? It'll be in your formula sheet. So Ag. So, where is Ag? Wow, it's so much. Okay, Ag is 107.9. So, imagine here, 107.9. Okay. So just oopsies. So, okay. So what's 0.54 divided by 107.9? And that's 0.05. So 0.005 mole. And we know it because it's a 1-to-1 ratio, it should be equal to the number of mole of electron. This is not equal to that, so that's rubbish. It's not this solution. And yeah, we will try this method for all of them pretty much. So the next one, let's try the next one. So the next one is, of course, nickel, which has nickel 2 plus 2 electrons becomes nickel solid. So imagine we have nickel solid, so 0.54 grams divided by, what is the molar mass of nickel? So nickel has what? Nickel 58.7. So okay, so let's put that there. So we have 0.54, so 0.54 divided by 58.7, and that gives me 0.0091 mole. This is the number of moles of nickel. And remember, we want to find the number of moles of electrons. So using this, because, by mole ratios, it's just times them by half, so 0.5. It is 0.045. It's not the same as this, so also that is not good. Let's try the next one. So this one will be Pb2 plus 2 electrons goes to Pb solid. So if we have 0.4, what's the mole of Pb? Pb, where are you? 207.2. 207.2. So let's use that and see if that gives us an appropriate answer. So imagine, so 0.54 divided by 207.2 and imagine timesing it. So yep, that's going to give me the number of moles of PB. Now to get in terms of electrons, we just need to multiply by half because, you know, using your mole ratios. And that's going to give me 0.013, not the same as that, so not good. I would say it's D. In a real exam, I'll just, you know, choose D quick, but let's check if it's D also. So chromium, just C3 plus in this case, 3E goes to C3 solid, so it'll be the number of moles of chromium is 0.54 grams divided by, what is the molar mass of chromium? Chromium has 52, so alright, so 52, so 0.54, 52, and because we times it by 1/3, and that's going to give me the mole ratio, so 0.03, perfect. So pretty much the same as this. It's the closest one that has this. I want to make sure to double check, so did I do everything right? Have I explained everything? So 52, yep, so you know 0.54 grams divided by the mole mass, and then times it, that's going to give me my mole, and I times it, times it by wait, what am I doing actually? What? Wait, I've made a big mistake. A stupid mistake. No, guys, please be careful. I may have done all of this wrong. Because what I'm supposed to do in mole ratios, for example, this is Ag, plus E minus. For the first one, if I want to find the electrons, this one, it was easy. This one was a 1-to-1 ratio. It doesn't change the answer. But the other one, because they, for example, this one was a nickel 2 plus 2E, nickel solid, I'm supposed to multiply by 2, not half, because I want to get to the electron. What is the mole of electrons using this? So it'll be 2. Yeah, so okay, so just let me do that quick. Actually, that's a stupid mistake, because yeah, so what's nickel again? Oh, I hate looking for these ones. Oh my god. Nickels is 58.7. So again, so 58.7. So what is 0.54 divided by 58.7, and imagine you can times it by 2. That is 0.018, not the same as 0.03. That's wrong. Easy. So I need to check if it's also C then. Same thing. Easy. So what a stupid... I don't know what I just did. It's right now 3 o'clock and yeah, man, just lost it. 2 plus 2 electrons goes to PB. And so it's going to be also multiplied by 2 to get that. So imagine that. So what's 0.54 divided by PB? So lead is 207. 207.2, and imagine multiply by 2, that's 0.052, so not C. So it can only be D. Let's check D also. So remember, chromium is just, let me rub this out. Chromium is this. So imagine, 0.54 divided by the chromium. What is chromium again? 52. I times it by 3. Aha, now it's the same. So it's 0.0310. So it's D as your answer. Wow. Yeah, D is still the same actually. Yeah, but such a stupid word. Don't do what I did there. I accidentally, remember when you're trying to find, for example, if I have the number of moles of chromium, which I have when I calculated, so if I want to find the number of electrons using the chromium, number of moles of chromium, remember, it's going to be multiplied by what you want, which is the electrons, which is that coefficient, divided by which one did you use, which is this one over here with coefficient 1. So it's always multiplied by 3. So So D is your answer. Sorry for the confusion. That was, yeah. I hope that makes sense. 25, that took too long for that one, actually. A certain fuel contains 91% octane by mass, with the remainder being ethanol. When 2.5 kilograms of the fuel is completely burned at 25 degrees Celsius and 100 kilopascal. So this here is SLC, by the way, because 25 degrees Celsius and 100 kilopascals is, yeah, standard, normal. The amount of energy produced in megajoules would be nice and easy. So if I have, 2.5 kilograms of that fuel, well, let's convert it to grams because that's much easier to deal with in chemistry. And I know 91% is octane, so imagine timesing it by 0.91. So 250 times 0.91, and that's going to give me 2275 grams of octane. Whereas, again, the rest of the other one, so that 2,500 minus 275, the rest, which so what am I doing? So the rest minus 2275, the rest, which is 225 grams, which is ethanol, and I want to find the energy. And that's easy because as CLC, we are luckily given in our data book. For example, let's look at octane. Octane, where are you? So octane is over here. So in this case, octane, and we're going to look at where is octane? So octane's that. It's this one over here, the heat combustion in terms of grams, because remember we have them in terms of grams. So if I have 2275 and I multiply by this constant over here, 47.9, that's going to give me in terms of kilojoules how much energy will be released. So I'm going to write that here. So that's 108,972.5 kilojoules plus how much kilojoules of energy would ethanol will produce. Well, again, where is ethanol? Ethanol's over here. So if we have 225 times that 29.6, that's going to give me 660 kilojoules. Imagine adding those up, and we want to convert it into megajoules. Remember, the answer is in terms of megajoules. So let's add them up. So 108,972.5 plus 6660. Okay, so we got it in terms of kilojoules. Imagine timesing it by 1,000, so we convert it into joules, and then dividing it by 1,000,000 to get it in megajoules. Is that perfect? That's going to give me 115.6, which is 116. So 25C. The concentration of propanoic acid, which is this solution, was determined by titration with standardized sodium hydroxide. So, okay, solution at 25 degrees Celsius. The reaction for this titration is shown. Perfect. A 0.1 mole solution of sodium propanoate, which is that, in water has a pH of 8.9 at 25 degrees Celsius. The most appropriate indicator to use for this titration would be what? Such a beautiful question because, they've given you the pH for this over here, which is going to give you where the end point is going to happen. So if you look at your formula sheet, luckily we have the pH. So if you look at your pH over here, where is our pH? pH values, where is it? Here. So acid-base indicators. So because we're saying 8.9, where is 8.9 in the pH ranges? 8.9, it's around this one over here. 8.9 is around there. So the this one is the one that you're going to use. Thermal blue, second change. So thermal blue would be the best indicator to use here. Choose A, actually. Yeah, 26A. Easy. Nice and easy. Question 27. Tricserin, a triglyceride, is the primary fat found in beef, and it contains stearic acid as the only fatty acids. All right, so you know, a triglyceride has a backbone of glycerol. So, and like, you know, 2 double O's here, and so wait, if it has 3 acids, we're gonna have. So here would be stearic acid. One of them would be stearic acid, because only the fatty acid that is stearic acid means that all of them have, the three fatty acids are going to all be stearic acid. So, okay, that's your triglyceride. 100 grams of pure sample of triglycerine, which is this triglyceride, is completely broken down into its component molecule, glycerol, and stearic acid. Okay, remember when we said, when fats gets broken down, the only way they get broken down is for hydrolysis. So, let's talk about it. So, if we had triglycerine plus water, which is, how much water molecules do we need? Well, we need 3 always, because remember, we're going to have to break this bond, and this bond for hydrolysis. We're going to need 3 water. And it should give us what? It's going to give us 3 stearic acid. So remember, now imagine breaking this down. You break this down. So we're going to get 3 stearic acid plus how many? 1 glycerol backbone, pretty much. So 1 glycerol backbone. That's it. So using these, the reaction will produce what? Okay, so the first one says produce 3.10 grams of glycerol. How do we check that? Okay, if I have 10 grams of pure sample of triglycerine, so imagine 10 grams divided by the molar mass of triglycerine, which is 890, is given here. That, and we're going to use molar ratios. Well, to find the mole of glycerol, it is a 1-to-1 ratio, as you can see. 1-to-1 ratio. So it's going to be the same mole, and I'm going to multiply by its molar mass to get it in terms of grams. So times 92. So for this reaction, it will produce 1.03 grams of glycerol, not 3.10 grams. So A is wrong. Next was requires 0.836 liters of hydrogen gas. Where the hell did they get hydrogen gas here? There is no hydrogen gas. It's wrong. Requires 0.0112 mole of water molecules. Okay, so the way we do this actually is, so requires 0.2 moles of water molecules. Okay, so again, same thing. So 10 divided by 890 to get the mole of triglycerine, and then we want to find the mole of water, which is multiplying it by 3/1. So it's a times it by 3, and that's gonna give us 0.0. We'll get 0.0337 mole of water, not this. So let's check the last one. Produces 2.03 times 10 to the power 22 molecules of stearic acid. Let's check that. So again, so it's going to be again 10 divided by 890, and so to get to stearic acid, it's going to be timesing it by 3. So it's a 3-to-1 ratio. So we get that, and so what we're going to need to do is we want molecules. So we're going to multiply by Avogadro's number, which I don't even know what it is. So it's in your formula sheet. So where's Avogadro's number? So it should be here. We haven't used Avogadro's number for so long, actually, because it's normally in unit 1 and 2. So it's normally in year 10. Year 11. So 3 times 10 to the power 23. And that's going to give me 2.029 times 10 to the power 22, which looks like D is your answer. Beautiful. I hope that is easy. That's nice. All right, question 28. Dissolved carbon dioxide CO2 can react with water H2O to form carbonic acid. Okay, so carbonic acid can also react with water to form bicarbonate ions and hydrogen ions. And here are the reactions. Okay, a beaker that contains 2 liters of deionized water is placed in a room and left overnight so that these 2 reactions reach equilibrium. In the morning, one change is made to the system. Which of the following changes is most likely to result in an increased concentration of H3, the hydronium ions? Okay, so when she put, a beaker that contains 2 liters of deionized water, so imagine normal water, which is that H2O, and because I think the atmosphere has CO2, so it's going to react with that water, and it's going to create this, and this react again with water, and it gives us these 2 products. That's what's happening. So let's look at what will increase the concentration of H3 ions. We want to increase this concentration of that. So the first one is dilute the solution. What's happening if we dilute the solution? Imagine diluting solution. You're increasing this H2O. If you're not diluting solution, you're decreasing the concentration of CO2. And the system's like, hey, you're decreasing it too much. I'm going to need to compensate for that. So I'm going to go backwards to increase my CO2. And if it goes backwards, what's happening with this H2CO3? It's decreasing. If that decreases, let's go back to the second equation. So that's decreasing. And then reaction's like, wait. This H2CO3 is decreasing. I need to compensate for that. So I'm going to move the reaction to the left, to increase this. So what's happening? Well, the H3 will decrease because we're moving to the left. So that's not a good way. That's not increasing the hydronium ions. That will actually decrease it. So nice and easy. That was all right. Bubble in more CO2 gas. Let's think about it. So if we're bubbling more CO2 gas, we're actually increasing the concentration of CO2 gas. And then the reaction, so the system's going to be like, hey, that's so much, that's too much. So I need to compensate for that. So I'm going to, move my reaction to the right so I can decrease this concentration. So if it's moving to the right, we're increasing H2CO3. So imagine increasing this over here. And then again, if it's increasing, H2CO3, it's going to be like, it needs to compensate for that, so it's going to move to the right. And if it moves to the right, we are increasing the hydronium ion. So B looks beautiful, actually. B looks nice. Add a few drops of phenylphenol, I can't even say that, indicator. No, indicator doesn't do anything, by the way. You should know that. Add a few drops of 0.1 mole of sodium hydroxide, NaOH solution. No. If we're trying to increase hydronium ions, which makes the thing more acidic, and we're adding something like sodium hydroxide, which is one of the highest basic, it makes it basic pretty much. Adding a small drops of this will decrease the hydronium ions. So possible answer would be B. 29. So the following diagram represents the operation of a secondary cell during recharge and discharge in no particular order. The diagrams of these circuits are not complete. Okay, so what do we see? So cycle 1 has okay, so the electrons are going from the negative to positive, so this is discharge here. And this one has to be recharge here, because it's going from positive to negative. Okay, what else do we know? So we know, because this is negative, this is going to be the anode here, where oxidation will occur. This is the cathode, where reduction. So red, in this case here, don't be fooled. If this is negative, it's going to be your cathode. So this one over here is your cathode, and this one here is your anode. All right, so which of the following correctly describes the cell and its operation? Cycle 1. So cycle 1 says, okay, energy is produced. Yes, energy is produced. Remember, a discharge is you're converting chemical energy to electrical energy. So energy is produced, electrical energy is produced. So that's great. And then cycle 2 says, for cycle 2, anode is positive. Yes, the anode is positive. So that's correct. And the next one, B, a spontaneous reaction. Yes, so when a discharge happens, it is a spontaneous reaction, so we can tick that. Energy is produced in cycle 2. No, energy is consumed in cycle 2 because it's recharging. So B is wrong. C, anode is positive. So nope, anode is negative. So D, a spontaneous reaction. True. And a cathode is positive. Remember, cathode in this case is negative. So A is your only answer in this one. Nice and easy. Last question. Wow, very tiring. Cold weather can affect the performance of diesel fuels such as petrodiesel and biodiesel. You should know that. Remember, when cold temperatures, biodiesel has a high viscosity, meaning that it doesn't flow through fuel lines, whereas petrodiesel does flow nicely. As the temperature is lowered, so you're decreasing, so making it colder, a point is reached at which the larger molecules in the fuels begin to solidify out of the liquid. When this point is reached, the fuel starts to become cloudy. The temperature at which this point is reached is known as the cloud point. Which statement is correct? So pretty much cloud point is when it becomes like a slushy. I think so. Just from what it's describing. So if a fuel's becoming like slushy, if it has a high, cloud point, it will likely be biodiesel, because biodiesel is a problem when it gets the temperature decreases. It becomes hard to flow because it has a high viscosity. So it probably have a high cloud point because it probably becomes a slushy, from what I think. So which statement is correct? High cloud point indicates that the diesel fuel is a biodiesel. True. Okay, that could be true, and will produce more pollutants. No, absolutely not. Petrodiesel produces more pollutants than biodiesel. B, a low cloud point indicates that the diesel fuel is a biodiesel. I would say no, because remember, a high clouding point indicates that the diesel should be biodiesel, not low cloud point. So yeah, so if it's cloudy, it means it's freezing pretty much. So I wouldn't say, yeah, B is wrong in that one, because it should say a high clouding point for biodiesel. See, a low cloud point indicates that the diesel fuel is petrodiesel. Okay, yeah, low cloud point, and will flow readily, so easily in cold temperatures. Yes, petrodiesel tends to flow easily in cold temperatures, because only it consists of dispersion forces. Whereas biodiesel has a ester group, so it has what we call a dipole to dipole. So C looks very good. So I would put C as your answer. What about D? A high clouding point indicates that the diesel fuel is a petrodiesel. Wrong. Remember, high clouding point would probably indicate that it is a biodiesel. So 30C. And that's it, guys. I hope you guys enjoyed this video and learned something through this video. Please make sure to like and subscribe and share this video with your friends. Have a great day, guys, and take care of yourselves.